Hi, this is Robert Quimby, and I'm going to tell you about statistical distributions. What can I say? It's a random universe that we live in, and as astronomers, you need to understand how this works, and you need to understand that sometimes you're going to go and you're going to take a measurement, and then you're going to do the same exact experiment again, and you're going to get another measurement, and you might get different results for those two quantities that you measure. Sometimes people chalk this up as experimental error, right? They say error, but it's not an error in the sense that you did anything wrong. This is just the uncertainty from nature showing up in your experiment. So what we're going to do in this tutorial is we're going to start by just considering this randomness of nature and how that can impact your results, and to appreciate that this is not an error that you've done, that this is actually just the uncertainty of nature. Next, we're going to roll the dice and see what the outcomes are and learn how to predict what the odds are of getting different outcomes. And once we've established that there is a range of possible outcomes for any given experiment, we need to quantify what that distribution of outcomes looks like. And we're going to talk about the most important distributions in astronomy, the Poisson distribution and the Gaussian distribution. And we're also going to cover the binomial distribution, which is at the heart of all of these. So as always, this is just going to be a quick introduction to these concepts. If you want more details, the kind of classic paper at the graduate level is not paper, this is a book, Data Reduction and Error Analysis for the Physical Sciences by Bevington and Robinson. There's also another text that's a little more targeted towards upper division undergraduates and beginning graduate students, an Introduction to Error Analysis by Taylor. So check those out if you want to go over the math in more detail than we're going to do here. All right, so let's get started by doing a kind of a thought experiment here. I want you to think about taking a teaspoon with you next time you go to the beach. Go down to the sand, take a scoop full of sand, getting your teaspoon, kind of level it off, and then take that teaspoon and dump it onto maybe a piece of paper or something, and one by one, counting each one of the grains in the teaspoon. I don't know who would actually do this, but if you did, you could get a number for how many grains of sand were in that teaspoon. And then you could repeat the experiment. You can toss those grains of sand aside. You can get another scoop of sand. You can do the same process, level it off, dump it on a piece of paper, count each grain. And when you get to the end of there, probably going to get a different number than you got the first time. And this doesn't mean, again, that you did anything wrong the first time or the second time. It just means that you're seeing the randomness of nature show up in your measurements here. So when you think about it, each one of those grains of sand is pretty unique. It has its own history about how it was formed and how it was shaped and the random processes that were involved in creating it. And you're going to get some distribution of different sizes of grains of sand, and they're going to pack together differently depending on how they're oriented. So you're going to get a different number in that teaspoon. And so just from all these different random processes all mixing together, you're going to get slightly different results every time you do this experiment. To save you the trouble of actually going to the beach and doing this, I've created a little file here of kind of simulated trials. I didn't do this myself, but just simulated results in this media folder sand.dat. And we're going to load this in with gen from text here, and then we're going to plot. All this file has is just like the number that you would have gotten if you had done this experiment many times. And we're going to see what those look like. So we'll plot this up here. And so here now, this is for each sample that we tried. So it looks like we did 100 different trials here. In each trial, we see how many grains of sand, we count them all, and there's some scatter here. Every time we do this experiment from all these random processes in nature, we get a slightly different result. And that's fine. It doesn't mean you did anything wrong. Again, it's just that's nature showing you its random side. So we can see from this that there's not actually a simple answer to our question, how many grains of sand are in a teaspoon, because every time we do the experiment, it's going to be a different number. So what we really want to know is what is the distribution of values that we're going to get in our teaspoon, and maybe what's the average number. So we can calculate what the mean value is for these. So we'll take all the samples that we loaded. We'll just calculate the mean for all of those, and that'll give us some kind of an idea. So if I said when you go to the beach, and you take your teaspoon, this is how many I'd expect that you would get. But it's not going to be the exact value. There's going to be some scatter in that. So I should also report to you what the range of possible outcomes is going to be. And so what I'm going to do here is I'll calculate the standard deviation. And that's just what's the typical offset above or below the average value of all these outcomes. So there's a nice little function in NumPy that does this for us. So we can just take our samples, object, and we'll just use the standard deviation function there. And I'm going to set the delta degrees of freedom to 1. And we can print this out. And it'll tell us that when you go to the beach and you repeat this experiment, you expect to get 860 grains of sand. But if it was 700 more, 700 less, I wouldn't be surprised. It's just randomness in nature. So hopefully this little thought experiment has made it clear that when you are presenting the results of some experiment you've run, you don't want to just give one value. You want to say, this is the answer to my experiment. What you want to do is you want to present the range of possible outcomes that others may encounter if they repeat your experiment. That way, if someone does repeat your experiment and they get a different answer, you can say, well, that's actually consistent with mine. That's consistent with the distribution I would expect. So to understand what the distributions you expect might be, we got to get a little bit of better understanding of what the statistical properties are of random samples. So to do this, we'll begin by playing dice. So here's a simple question for you. If you got a regular 6-sided dice, not that like 20-sided stuff you do with Dungeons and Dragons and all that, just a regular 6-sided dice, and you roll the dice, what's the probability that you will roll a 3? You should probably be able to figure this out pretty quickly. There's 6 sides to the dice. So, okay, there's a 1 in 6 chance that I'm going to get a 3. And that's the answer to the question. Let's make it a little more tricky here. What if I have 2 dice? And I say, okay, I'm going to roll both of these at the same time. And what I want to know is what is the probability that both of those dice are going to come up with 3s on them? Slightly more complicated, but you might be able to figure this out as well. You start off by saying, well, the first dice has 6 sides to it, so there's a 1 in 6 chance of getting a 3. Second dice has 6 sides to it. So again, there's a 1 in 6 chance. And to figure out what the probability of them both being 6s, you just multiply those 2 probabilities together. 1/6 times 1/6, and you get your answer. The probability of getting exactly two 3s on your 2 dice is 1 in 36. So let's make it just slightly more complicated now, and this will really get into how nature works here. Instead of saying, we're going to do the same experiment now. We're going to roll 2 dice, but the outcome is going to be different. So what I'm asking now is, what is the probability that it will roll exactly 1 3 on those 2 dice? So spend some time and actually think about this carefully now. This is really at the core of how all of the randomness of nature is working. So you really need to discover this for yourself. I can tell you the answer, and I will in just a second, but it's much better if you can figure it out first. So pause the video and think about what the answer to this question is. Okay, do you have your answer? If not, you better pause and do it. All right, let's work through the answer here. So this is actually the same kind of problem we just did. Let's just work it out. So I got 2 dice. I roll the first one, and there is a 1 in 6 chance that I'll get a 3. Okay. Now I roll the second dice, and most of the outcomes on that dice are not going to be a 3. In fact, 5 out of 6 options are not 3. So that means the probability of not rolling a 3 is 5 out of 6. And we do just like we did before. So we have 2 dice, 2 probabilities, I should say. The first one is 1 in 6. The second probability is 5, 6. And we can multiply those together to get our probability of rolling 1, 3. But there is one more step we have to consider here. We have to remember that we have 2 dice. And the question is, what's the probability of getting 1 3? Not just getting a 3 on the first one and not getting a 3 on the second. So there's actually 2 ways to get a 3 on one dice. We can get a 3 on the first dice and not on the second, or we can get a 3 on the second and not on the first. So we have to multiply this by 2. And if we do that, this is actually the answer. There's about a 28% chance that we'll roll 2 dice and we'll get exactly 1 3. So all that's left to do now is just generalize this. So instead of having 1 or 2 or 3 dice, let's say we have n dice. And instead of rolling 1 or 2 or 3 3s, let's say we roll k 3s. So we want to figure out now, given n dice and we want to get k3s, what is the probability of that happening? And the way we can solve this is with the binomial distribution. So this may look familiar. You may have covered something similar to this before in your studies. Let's just go over what we got here. So we have kind of three different parts to this, this equality here. So there's this part here which relates to your probability of getting a successful result. So success means, if we're trying to roll 3, we get a 3. That's a success. And the number of trials we have here, n, that relates to like how many dice are we rolling. So if we're rolling 5 different die and we want to get a 3 on one of those, we want to have one success. So the probability of getting a success on each one of those dies, p here, is just 1 in 6. And then we're going to multiply it by the probability here of not getting a 3 on all the other dice. All right, so this is 1 minus the probability of getting a 3, 5, 6, as it was before. And this is n minus k, that's the number of dice we have left after we've done the dice that we want to have successes on, we want to get a 3 on. And then the last part, again, is just this factor here, this coefficient, and this is the binomial coefficient here. We just use it here so that we can calculate what that degeneracy is, like how many different ways can we order our results here and get the same thing. So, if we're trying to roll 1, 3 on one die, and we have 3 different dice, well, there's 3 different ways we can organize that so that one die that we care about is ordered first, if you want to think of it that way. So we need this coefficient here, and we need the probability of success and the probability of failure. Multiply these all together, and you got your binomial distribution for any k value you pick. So let's put this to work here. So let's now roll 3 dice instead of 1 or 2. So we'll roll 3 dice, and we're going to use the same kind of dice, but I have 6 sides on it. So the probability is going to remain 1 in 6 of getting whatever number we want. Maybe we want a 3 or a 6 or whatever we want. Not a 1 in 9, 1 in 6. And then what we need to do is calculate this probability here. Given our n and our p value, we can pick a k value, and we can calculate this probability. So instead of just picking one k value, I'm just going to do all the possibilities that there are. So if I use numpy a range and give it n plus 1, that will give me 0, 1, 2, 3, and 4. Not 4, 0, 1, 2, and 3, which are the number of k values that are allowed if n equals 3. And then we can calculate for each of those what the probability is, the binomial probability is. So we can go back to this equation that we just did, and we can actually code this up in Python if you want, but there's a shortcut here. It turns out that there is this package scipy, and in it there has a sub-package called stats, and that has a little module called binom, which is going to give us the binomial distribution that we care about. So I'm going to use binom, and I'm going to use a method it has called PMF. It stands for probability mass function. So we're going to use it to calculate a probability, and this here, the result here is called a probability mass function in statistics because we're calculating the probability of getting some result, and the results are discrete. It's not a continuous distribution. It's only valid for integers n and k. So we're going to use this probability mass function. We got to tell it the k values that we want to calculate the probability for, and we got to give it what the number of trials we have is and the probability of success for each one of those trials. And then when we run this, it'll calculate the probability at each one of those k values for us. Okay. So now we can plot this up, and I'm going to use a bar plot here to show you different values. So for each k value, we're going to see what the height of the bar is, and that'll give us the relative probability here. I've got some other stuff here to make this plot look pretty, but let's just run it and just show it. So here we go. And so here are the different possible k values, 0, 1, 2, and 3. And this is the probability, according to the binomial distribution, of getting that number. So in this case, if we wanted to know how many times are we going to roll the dice, all 3 dice, and get no 6s, well, 58% of the time, that's going to happen. And what if we roll 3 dice and we get 1 6? Well, 35% of the time we expect that to happen. 7% of the time we're going to get 2, and very rarely, only 0.5% of the time, are we going to get the Yahtzee. We're going to get all 3 dice have 6s. So you might ask, if you're a gambling person, you want to know what the odds are here. What is the expected number of 6s I'm going to get. And by that, I mean, what is the average? So if I do this experiment many times, on average, how many 6s am I going to get? So this is called the expectation value. And the way you calculate that is you take the value that you get, so this is 0, 1, 2, or 3, the k value basically, and you multiply it by the probability of getting that k value, and you sum this up over all the different possible combinations, and that's going to give you the expectation value. So this is just a weighted average of all the possible outcomes. So in this case, I'm writing f of x, but I've already told you that for the binomial distribution, that's just k. That's the value that you want to calculate the probability for. And then we can use this binomial distribution to calculate the probability for each one of those different values. And you can put this all together, and you could then figure out what the expectation value is. But it turns out if you just do a little bit of thinking here, you can probably figure out what the expectation value is without doing any of that. So if you think about it, we're trying to roll 6s now, and we've got 3 dice. Probability of rolling a 3 on one of those dice is 1 in 6. So if we roll 3 dice, how many 6s do you expect to get? It kind of sounds like it's just the number of dice we have times the probability, right? And it works out. That's actually right. That's the expectation value. So this is doing this equation here, doing the formal weighted average, right? If you work it out, you'll actually get a half, just like this. With a little bit of thought, you can do it without doing the extra math there. Let me support this. So I haven't derived this for you, but I'll just show you that this is the case. So in that package, in the NumPy package, there's a random package for generating random numbers, and there's different types of distributions of random numbers. We want the binomial distribution. And so if we use this little function here, we can tell it the number of dice that we're rolling and the probability of getting what we want on each one of those dice. And then we can draw randomly from this distribution. So this is going to make a distribution of values for us, and we can just randomly draw numbers from that distribution. I'm going to draw 10,000 numbers from that distribution. And we'll have all those numbers, all 10,000 numbers stored in this variable here, bdist. And then we can calculate what the mean value of that is. And that should be our expectation value. So we're doing lots and lots of different trials. And expectation value by definition is just what is the average of lots of trials. And so if we run this, we get a number that's very close to 0.5 here. It's not exactly 0.5 because this is a random process. If I run this cell again, I get a slightly different number. And every time I run it, I'll get a different number here. All right, so this is great if you're going to Vegas and you want to know what the odds are at the craps table, but as an astronomer, you're probably looking for slightly different kind of distribution here. The distributions that we tend to look at are things like you have a big cloud of gas and some fraction of the atoms in that gas are excited. And, you know, if you have an atom in an excited state, there's some probability that at any given time, you'll get a transition down to the ground state, and that will release a photon. And as astronomers, this is what we care about. We want to measure photons. So if we have some big cloud of gas, we might want to wonder, well, what's the probability of me getting a photon or getting some number of photons, 100 photons from that cloud of gas in some given time interval. So let's do kind of a little experiment here. We're not going to actually simulate total number of excited atoms in a cloud of gas, because if you think about that, that's a cloud of gas could have trillions and trillions and trillions of atoms in it. That's a little more work than I want your computers to do today. So we're just going to pick a million. We're going to have a million little test cases here, little trials, little atoms if you want to think of it that way. And we're going to set the probability that any one of those atoms will have a transition in some period of time at 2.5 times 10 to the minus 6. So we'll give it a very slight probability in a little time window that it's going to have this transition. And then we'll use the binomial distribution. We'll use that probability mass function again, and we'll calculate for all these different k values. We'll calculate the probability given the number of excited atoms we have and the probability of transition for any given one of those atoms. So let's take a look at what this distribution looks like. This is something that's more appropriate for an astronomer to know. So we're going to do the same thing again. We're going to plot a bar graph here and pull that up, and here's what that looks like. Now, A couple important things to note here. So this is the number of photons we've detected by our experiment, going from 0 to 4, 6, up to about 10 here. And you'll notice there's no negative numbers on here, right? It's impossible to get -1 or -5 because you can get 0 photons, you can get 1, you can get 2. You can't get 2.5 either. So there's only discrete possibilities for this outcome. And for each one of these now, using the binomial distribution, we can calculate the probability. So we know now if we have this cloud, it's got 1 million excited atoms, we know their probability of a given atom decaying and producing a photon. This is going to tell us the number of photons we expect that cloud to be emitting at any given time. So what is that expectation value? So we can calculate this actually pretty much the way that we did before. It's the same kind of setup. We've got a cloud. We know it's the number of trials that we're doing. We know the probability of each trial. So the expectation number, again, is just n times p. That's it. And just to double check, we can again do our binomial distribution. So we'll do our NumPy random. We'll use the binomial distribution, and we'll give it the n, the number of trials, the probability, and we'll do it 10,000 again, just to make sure these two both get the same answer roughly. And as you might have guessed, given the numbers that we started with, we expect to get 2.5 photons emitted by this cloud. And in our little simulated trial here, that's about what we got, 2.5. Okay, so this distribution here, it has a particular shape to it. You'll notice that, again, it's asymmetric. It's got this nice tail going onto larger numbers, but it can't have that tail on this side because it's impossible to go to negative values. So it's an asymmetric profile here. And this is a distribution that's very important in astronomy. And it actually, if we have a large enough number of trials, number of atoms in our case, we get a special distribution, which is called the Poisson distribution. So this distribution is very handy because it has a simpler formula for calculating it. So if we are in this case when n is large, instead of using the binomial distribution formula, we can use this formula here. So in this case, we just take that product, n and p, that's giving us our expectation value, and that's the only thing we need, just that product. So just with that product, that one number, for any k value you're interested in, we can calculate what the probability is. So I'm not going to derive this equation and show how it actually falls out if you start with a binomial distribution and go to n of infinity. There are other texts that you can check to do this. Well, what I'm going to do is I'm just going to show you. So we're going to again plot that same bar plot we had before for our distribution. And then on top of that, let's use SciPy stats here. And we're going to plot a Poisson distribution on there. So the way we do this is we use Poisson. And again, there is a probability mass function, PMF. And all we have to tell it now is the values we want to calculate the probability for, the values of k, we want to calculate the probability for. And I'm just going to use the ones that are positive, are relatively large probabilities. We calculated 1 million different probabilities here, but not all of them are very important here. And then we just need to give it that expectation value, which again is just n times p. And we can plot this up. And there we go. So I haven't derived this, but hopefully you can see here that these points at the top of the bar here are met very well, very nicely by this Poisson distribution here. So in fact, for large n, we get a Poisson distribution from a binomial distribution. But the same mechanics are at heart. It's all just rolling dice when you get down to it. So what if the product of these two numbers is large? This is another case you might get in astronomy if n times p is large. So let's take a look at that. So what we're going to do is we're going to start off with the expectation value we had before, n times p. And we're going to multiply that by 100, just to make it a larger number. And so now, again, we can calculate our Poisson distribution. It's our probability mass function. And we're going to give a bunch of values to calculate. We'll do NumPy A range, A-R-A-N-G-E, and we'll do 2 times our expectation value just to get that many different possibilities. So these are our k values here that I've just put in there. So I'm just going to do numbers from 0 to 200 for our k values. And for each one of these, we need to tell Poisson what our expectation value is. That's the number here. And if I plot this up, there we go. So this may look a little bit different than the plot before. Previously, we had this very asymmetric shape here, right? But you'll notice now it's actually quite symmetric, right? It's centered still at 250. That's what you'd expect, right? But it turned into a very symmetric distribution. And of course, looking at this, you've probably seen this distribution before. This is a very common distribution to get in nature. And of course, what this distribution is a Gaussian distribution. So let's go ahead and show that. So again, I'm not going to derive this. I'm just going to show it to you. So we're going to use SciPy stats again, and it has another distribution package, norm, and that's for normal, because the Gaussian distribution is the most normal distribution you're going to get. So we call it the normal distribution. So let's use the norm here, and we're going to use this time the probability density function. So it's not a probability mass function now, because we're actually going to move into continuous function. It's not discrete, it's continuous. So for this function, we have to tell it the x values that we want to calculate this for. So this is not k values. I'm switching variable from k to x because this is not discrete. And each one of those x values, that's going to range from 1 to 500 here. I'm going to have 1,000 of those values. We're going to calculate what the probability from a Gaussian should be, given our expectation value. And then we need to know what the width of this distribution is. This is actually an important point I'm going to go back to here. When we switched from a binomial distribution into a Poisson distribution, remember we went from 2 variables to just 1. So this one variable here, just mu, the expectation value, sets not only where this peak is, but also the width of this distribution. Somehow that information is all encoded in just in that one number there. And so there's actually a very handy relationship between the width of this distribution and its expectation value. And that turns out to be the width of the distribution is just the square root of the expectation value. We plot this up. We can see indeed this green line here on top of the red dashed line looks like it's doing a pretty good job of representing the Poisson distribution we have. So it's not a perfect fit here, right? Notice if you look carefully, it's a little bit off, but that's just because our expectation value is 250. The lower we make this number, the more it's going to look like a Poisson distribution and the less it's going to look like a Gaussian distribution. But in the limit that we allow mu to go to infinity or go to a large number, it very rapidly approaches a Gaussian. So by 250, it's already very much a Gaussian. If we go to 2,500 or 200,000, it's going to be virtually indistinguishable in its shape, except now the Gaussian distribution is continuous. We can calculate for any value. You can calculate for 100, you can calculate for 100.01, 100.02, any number you pick. So this is the equation you've probably seen before for a Gaussian distribution. It's the natural number here, e, raised to the exponent of x minus 2. So x is whatever value you want to calculate the probability for. Mu here is the expectation value again. You square that because it's a symmetric distribution. Divided by 2 times sigma squared. So sigma here, this is that value that we just calculated using numpy square root. So the for a Poisson distribution, the sigma value is just the square root of expectation value, mu. But for a Gaussian distribution in general, that doesn't have to be the case. You can have a Gaussian distribution which is not a Poisson distribution. You can just shift it along the axis anywhere you want. So if I go back, I can take this green curve here, and just by changing the expectation value, I can shift it left or right on this plot, but I can keep the width the same, right? So the Gaussian has 2 parameters in it, mu and sigma, and that gives you more flexibility. You can have different distributions there, and they're not always going to be a Poisson distribution. And there's this factor out in front, 1 over sigma times the square root of 2 pi, and this is just a normalizing factor. So in this case, I want to integrate this over all possible x values, and I want the total probability to be 1. So I need this factor here to do that. So hopefully that gives you a good sense of the different distributions that we're going to be dealing with, and enjoy.